When I teach a course in digital logic, I like to jump in and try to get to doing things with circuits as fast as possible. And so to make that happen, we need to have some basic understanding of binary numbers. Now, I think we understand why we need binary. We're using transistors. Transistors act like switches. And so on could be considered a 1. Off would be considered a 0, although you could make a different assignment. You could say off is a 1 and on is a 0, but traditionally we use this assignment for the binary numbering system. Okay, so we just have two levels. We've talked about why. It has to do with noise margin, so remember that aspect of it. But given that, let's move on to the next thing I need you to pick up quickly, and that is counting with binary numbers, or actually not necessarily counting, but representing numbers as decimal using binary. Okay, so in this example, we're just going to do 4 bits. With 4 bits, each of these 4 bits, starting with the least significant bit, LSB, moving up to the most significant bit, MSB, these have a positional weighting on them. So this is 2 to the 0, which is 1. This is 2 to the 1, which is 2. This is 2 squared, which is 4, and 2 to the cube is 8. So there's a positional system. So in this situation, I have 1, 1, 4, 8, and 4, 0 for the 2's place, and so that doesn't show up in this list, and 1 in the 0's place. And so you add those together and you get 13. And later on, we're going to cover hex in more detail, but hex 13 is represented by D. Okay, so one of the things I want you to get good at, and what you'll be good at the end of the course, is counting in binary, because we make truth tables by listing all the binary combinations, and we quickly come up with a decimal equivalent. So here is this infographic that you can play with where it counts through binary numbering and gives the decimal and the hex equivalent. Okay, so I'm wanting you to be fast at that so you can play around with this infographic. Okay, another thing that I want you to understand is that we often have sequences of bits that we use to represent numbers. And if you group these in different sizes, it's traditional to do that. There's some terminology I'd like you to know. So 8 bits is considered a byte, B-Y-T-E. I don't think I wrote that on this infographic. But then if you break a byte into 2 4-bit sections, those would be called nibbles. Okay, so this is the lower nibble and this is the upper nibble. Now I've got here 1, 1, 1, 1 in the lower nibble position. That takes the lower bit value, so this would be 15. So if I turn this off and this one on, now I have 16 plus 1 is 17. You get the basic idea. If I added this one, I'd now add 32 to 17 and get 49. That's the idea. So bit, that's 1 digit. Then we go to nibbles, which is groups of 4. Then we go to bytes. Oh, there's byte. Yes, that's on the screen. And then we can go all the way up to a word. And word is machine dependent. It depends on what processor you're using. So often people think of up to 64-bit words, okay, that are comprised of bytes. All right. So hopefully you start to memorize some of these patterns as well. We often use powers of 2, 4, 8, 16, 32, and so forth. And that gives us different ranges that we can use to represent numbers. We're going to go over this in more detail later in the course, but this is a quick start to get you going on this topic.